Hello everyone, my name is Bhargob Deka, and in today's video I'm going to discuss about my newly published paper, which is Analytically Tractable Heteroscedastic Uncertainty Quantification in Bayesian Neural Networks for Regression Tasks. And this paper is recently published in Neurocomputing, and the main highlights of the paper are that in this paper we address a new method that can allow quantifying aleatory uncertainty in an analytically tractable manner. And not only that, we also allowed that our method can handle heteroscedastic aleatory uncertainty, meaning that the uncertainty won't just be constant over time, which is homoscedastic, but it will depend on the input covariates that will pass to the neural network. And finally, it's a pretty minimal setup, meaning that the only changes that happen are in the output layer, and most of the equations as well as the code regarding the forward as well as the backward pass remains the same. So hence it is a pretty easy fit to the already architecture that we have, and I'll discuss more about it as we go forward. So before going into the method, let's understand what are the types of uncertainty that exist, because this is the main topic that we are trying to address. So let's consider that we have this function showed in red line, and we have these magenta points, which are the data. Now, and let's assume that the black line is our prediction represented by mu. Okay, and these are the uncertainty bound that exist. So basically the predictive uncertainty is composed of two uncertainty. So one is called the epistemic uncertainty, we see associated with the model parameters, which is represented by this blue bound here, and the aleatory uncertainty, which is the uncertainty associated that is present in the data inherently. So this is how both are represented, the aleatory as well as the epistemic. Now let's consider a case where we'll have much more data points compared to the previous one. So the figure on the right, the only change is that the function is the same, so we'll have much more data points, and the black line is the expected value that we have. So what will happen is that the epistemic uncertainty will shrink. So as we have more data points, the uncertainty regarding the model parameters will shrink, and it will identify what are the weights and bias that will be required in order to identify the true function. Whereas the only thing remains is this magenta bound here, which is the aleatory uncertainty, because this is the variability that exists in the data itself, and this we need to identify. In general, the epistemic uncertainty part we can obtain it analytically. There is a framework which has been developed in our group called TAGI, where we can obtain the epistemic uncertainty analytically. However, the aleatory uncertainty part is the computationally demanding, because we have to rely on offline approaches like grid search in order to obtain the optimal values for the sigma v, and then we can use it for our framework. So if we can have a scalable approach for aleatory uncertainty, meaning that an analytically tractable way of computing the aleatory uncertainty, then we can have a very scalable approach, because we already have an approach to quantify the epistemic uncertainty analytically plus the aleatory uncertainty. So we'll be able to scale to larger practical problems, and this is the problem that we try to address in our paper. Now I have spoken about the aleatory uncertainty. As I told you in the main highlights, we not only just handle aleatory uncertainty, we handle heteroscedastic aleatory uncertainty. Now, what is heteroscedasticity? To understand this, let's consider this function here. So we have g x1 x2, meaning it's a 2D surface with two input covariates x1 and x2. Okay, now let's just rotate this plane so that we are viewing from the point of view of x1, as if we don't have any knowledge of x2 anymore. So it will look something like this. Okay, let's remove the surface from here, and we'll see the data points like that. This meaning that there is some variability that exists depending on where you are in the input covariate, meaning that depending on the value of x1, the variability changes. So here we have like very minimal variability, whereas when we go from 0 to 1 there is large variability. And this is something that we call as heteroscedasticity, where the uncertainty or the variability in the data is dependent on the input covariate. And this happens mostly because we have a lack of explanatory variables, as we have seen here, because it's as if like we don't have access to x2 anymore, the second covariate, so it looked like this. And this is pretty practical. We'll have all the time that in real practical problems we'll never have all the explanatory variables in order to explain the phenomenon we are trying to model. So we'll always have to model a heteroscedastic aleatory uncertainty and not just the homoscedastic, which remains constant over time. So in order to solve both these problems, we have taken two frameworks and want to combine them together. So the first is AGVI, which is the approximate Gaussian variance inference. Now this framework provides us an analytically tractable way of quantifying variance by learning from each error instance. So as we see each observation and you have a prediction, so you can get an error instant, and from that error instant we learn what is the uncertainty or the variance term. And I have done a detailed video on this framework, and also the paper is available online. And then we have the TAGI, which is an analytically tractable Bayesian neural network. And TAGI doesn't depend on backpropagation, so we can do the end-to-end uncertainty treatment. So we'll have all the steps regarding forward as well as the backward in an analytically tractable way. So what our idea was to combine both of these framework together so that we'll have the sigma square v, which is the aleatory uncertainty or the variance that represents aleatory uncertainty, as a function of the input covariance. And we call this framework as TAGI-V. Now, before going into the TAGI-V framework, let's first see how the Bayesian neural network architecture looks like. So this is a feed-forward Bayesian neural network where we have the inputs here, and then we'll have all the hidden layers here, and then we have output unit, and all of these have their own distributions. Now the observation model that we'll have, this observation y will be equal to the z output plus an error term v, where this v is modeled as a Gaussian random variable with mean 0 and the variance term sigma square v. So this is the term that is modeling the uncertainty in the predictions. So finally, this is the full version. So we'll have all the input covariates, we'll have the hidden units, we'll have the output unit z output. Here we'll just have one, but we can also have multiple output units. Then we have the observation y, and we have the error term v, and you have already seen how the observation model connects the observation to z output and v. And finally we have the parameters grouped together, which are the weights and the biases. Okay, now let's represent this whole like the full form represented into a more compact representation shown by this, which is exactly the same as this one. Okay, now let's move on to the tractable approximate Gaussian inference, or TAGI. So in this, using TAGI, or in the TAGI framework, we can do the analytical inference for the parameters theta as well as the hidden units z, meaning that all the mean as well as the uncertainty variance associated with the parameters as well as the hidden units can be obtained analytically through algebraic expressions. If you look into the TAGI paper, all the equations are provided, as well as the package is already out there, which is called PyTAGI, and I'll provide a link in the bio so you can access, and you can see all the equations and everything. And there are the closed form expressions with which you can obtain all the probability distributions for the parameters as well as the units, and it doesn't rely on a back propagation system. And this allows it for to have an end-to-end treatment for uncertainty. But the issues are that, again, for the v, as you see that there is a sigma square v which is associated with it, it is expensive to obtain, as well as it is homoscedastic in nature. So we cannot infer or allow the model to have heteroscedastic aleatory uncertainty, and that limits its practical applications. So this is the TAGI network, which you have already seen. I'm just rearranged it like that because I'll add the TAGI-V framework to it. So again, the input covariate X, we have the initial parameters, then the first hidden layer, and then connected through the last hidden layer, then to the Z output, and then the Y and the V. Okay. Only change that happens is in the output layer, as I said. So here we'll have another output unit called V2 bar, which will have its own parameters represented by this. And then we need a way to connect V2 bar to V in order to close this loop. Okay. And this is what AGVI provides, that we have a term called V square. So we connect V2 bar to V square and then V square to V. Now, how all these operations happen, it is detailed in the AGVI paper as well as in the video if you are interested. So once we have done this loop, so in the beginning we'll have the covariates, so we'll have the weights and bias, and finally we'll obtain the values for Z output and V2 bar. And from V2 bar, which both will be distributions, so from V2 bar distribution we'll obtain this distribution for V, and then through the observation model it is connected. So we have observation Y, and then we'll update both Z output and V. Okay, and from V, using the equations in AGVI, from V I'll obtain V square, from V square to V2 bar, and then now I can update all the parameters theta, and combining with Z output can obtain these parameters theta L as well as for all the inner hidden layers. And that's it. This is the only change that happened in the TAGI framework. As I said, it only affects the output layer. And also the good part is that the total complexity would also be the same as TAGI. So it doesn't add anything to the complexity. So it makes it pretty minimal setup in order to integrate it to the original TAGI framework. Let's look at a toy problem now in order to understand the TAGI-V framework better, how it works. So I've considered this function of y equal to minus x plus 0.5 times a sine function plus v, where v is modeled as a Gaussian distribution where with mean 0 and variance sigma square v, and the sigma square v has its own function. As you can see that it depends on the input covariate x here. So this is how it would look. So the true function is here, which is the y equation here, and then the uncertainty, as you see, this is this equation here, sigma square v is equal to 0.45 times x plus 0.5. So it changes based on what the value for the x would be. Okay, and this is what you see here. So this would be the heteroscedastic uncertainty that we are trying to quantify. So let's consider these many data points for this, and then this is the network I considered for this problem. So I considered 128 hidden units and 2 layers of this, and then we have the output, Z output and V2 bar, and then we have the observation Y. Okay, and now when I pass through one epoch, meaning that we see the entire data set once, the results are not very good, because you see the black line, neither the expected value we are learning nor the uncertainty, and on the right we represent the log likelihood versus the epochs. Okay, but what happens if we move forward, see the data multiple times, which are known as the epochs? See that when we reach like 4 epochs, it's already getting better. So the expected value is getting better, as well as the predictive uncertainty is getting better. It's trying to learn what the actual uncertainty is depending on the input covariate x, and also we see that the log likelihood is also increasing. And finally, when we reach like epoch 28, which is kind of the optimal epoch in this case, we see that the expected value is correct, as well as it is able to understand what is the uncertainty that exists in the data. So finally, at epoch 28, we are able to identify the heteroscedastic uncertainty that is present in this toy problem. So moving on from the toy problem, let's look at this benchmark datasets called the small UCI regression benchmark. So this dataset, so there are 9 of datasets, and these are normally used in order to see how we perform against other methods or other Bayesian neural network methods that are also trying to solve the same problem. So here we compared with this number of methods, where these are pretty recent methods and these are published in really good journals. And we see that the method that performs the best takes the most amount of time. So the y-axis is the log likelihood, the x-axis is the training time in seconds, and it is presented in log scale. So this is what, and the blue is the PBPMV, and it performs the best while it takes a lot of training time. So it makes the practical applications a little bit less scalable because of this. And if we put our TAGI and TAGI-V into this, if you see, the TAGI is already on par with PBP as well as with Ensemble. So you can see that it already on par in terms of accuracy as well as in terms of training time. Whereas if you look at TAGI-V, even though it doesn't have a significant boost in terms of the log likelihood, however, it reaches the optimal log likelihood much faster. So it is the fastest in terms of reaching the optimal log likelihood in terms of the training time. So this is the advantage that we have with our approach, that it not only provides a way to quantify the aleatory uncertainty, it also provides us a very scalable approach while giving good predictive accuracy. So from the small UCI regression datasets, we move on to the large UCI regression benchmark. Now, this have, like as I've written here, 1 million plus parameters because it uses a large neural network of 5 layers. I have provided all the details in the paper and the whole setup, how to do it. And from this table here, where I present the log likelihood values for the 5 big data sets on which I tested, TAGI-V performs better in 4 out of the 5 data sets, and it is compared with most of the recent methods for Bayesian neural networks, and which are also performing really well. So we can confirm that TAGI-V is either on par or outperforming in terms of log likelihood compared to the other data sets, at least for the regression benchmarks. So finally, in conclusion, the strengths of TAGI-V is that we provided an analytical method for handling heteroscedastic aleatory uncertainty. So now we can have the epistemic as well as the aleatory uncertainty both handled in an analytically tractable manner. We have also provided multiple results where we see that it outperforms the original version, not just in terms of result, but also in terms of scalability and in terms of not relying on a grid search approach to obtain the sigma square V, which is very critical in order to have a good performance. And also that our approach is an order of magnitude faster compared to the existing inference methods, which is a big boost in terms of the scalability. So the limitations right now are that we are relying on a modified He initialization approach for the prior variances for the weights, where we adjust the gain parameters. In this paper, we did it using a grid search approach for all the data sets in order to have an optimal results. But going forward, we need to find a way to either set the gain values to something specific, or we find another initialization method in order to completely remove these gain parameters. Otherwise, this also becomes like hyperparameters that we need to tune, which we don't want to be doing. and also that we want to do much more tests, which was not possible in this paper. So we want to also address multi-output regression tasks as well as image regression tasks. That is something for the future. So this is what was done for this paper. Thank you.